Okay, hello everyone. Great honor to share my research about trustworthy machine learning, and today we'll with a focus on differentially private data generation and safety critical scenario generation. So actually in my talk I have two parts, as you can see from the title, and the first part I plan to introduce security and then second privacy. But based on the discussion just now, I would plan to change now, because I think the second part about privacy preserving data generation is still on a hot discussion right now in everyone's mind. I think it's very interesting to directly go to that. And thanks, Jared, for the nice context setup, and the application obvious, to my understanding and in my opinion, is very broad, and we can discuss more about that. And in terms of how we guarantee privacy, I have some ideas, and we can see here. And of course, there need further investigations from everyone. So, okay, first of all, we can see that indeed machine learning is ubiquitous in the world. It has been, we say, applied to any domains, like as large as autonomous driving, as small as your washing machines, and several security, safety critical applications like malware detection, biometric recognition systems, etc. But I work on trustworthy machine learning, and actually lots of times people ask whether or not currently there are real security and privacy attacks happens in real world. And here I want to give two quick examples, and we can go to how we can try to prevent them as a white hat together. So basically, in terms of the security perspective, in 2016, the White House Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked. And it actually, as Jeff just mentioned, affect the financial market, and the autonomous trading bot dump a large amount of stocks within seconds and swipe on about $130 billion within seconds. And this is so categorized as a fake news detection or the spam attacks. And this has been really happened in real world and caused real damage. And from the privacy perspective, many cases, for example, from the Australia airport, people already collect everyone's biometric information to do safety screening, which raises a lot of privacy concerns. So that's one application, say, with a lot of, say, medical data, like medical images and medical records, we need to do research on it so that we can predict what types of medicine, what types of treatment we should be used for different agents, right? But yeah, of course, we don't want to really use every identity's real information, therefore leak private information, so that when you go to your insurance company, people say, oh, you have this historical disease, so I will increase your insurance budget. So this is one case that we hope to protect your privacy so that your insurance is not raised up because of your privacy leakage, right? So, of course, there are many such real-world cases, and overall, it is called trustworthy in machine learning. And next, I want to briefly give an overview about what is actually trustworthy problem or gap in machine learning, and what's the key problems or key, if we ask one question that we want to solve in this big area, and what's that, and how different problems are connected together. So first of all, to my research couple of years and understanding, I think really the trustworthy gap in machine learning is distribution drift, and it can be categorized into different categories. First of all, in terms of robustness, I think many of you may heard this word, robustness, security in machine learning, right? Really, this can be viewed as the adversarial distribution drift, which means you can consider, in any way, Jared gave a good example, a very nice example about how we do machine learning, right? We train and we test, and usually we have this assumption that the training and testing data from the similar or even the same distribution. That's why we can do machine learning, right? We can make inference. But of course, in the adversarial environment, this will not be true. For example, in the training time, the adversary can manipulate the training data, which usually we call poisoning attack or backdoor attacks, etc. So it's very realistic, for example, in your Netflix recommendation systems or in your Amazon recommendation systems, people can create some fake account and draw some similar preference with you, and then add a lot of fake reviews and fake ratings, and then the recommendation system will be totally fooled. And similarly, during testing time, the attacker can manipulate the testing data distribution, so then generate this so-called evasion attacks, and which will show some examples in terms of from the data generation perspective. And the second pillar is privacy, as we just discussed. And this we can view it as inference, like distribution inference. So the first is adversarial distribution drifting from either training or testing purpose phase. And second is from the queries or any feedback you can get from the model, right? As someone has asked, if I ask the model and the model give me some feedback, I can guess some statistics or some private identity information from the training data distribution, either membership, usually we call membership attack, or either the actual training data information we call model inversion attack. You can recover the whole model, you can recover the whole training data from some feedbacks of the model. So we have several couple of model inversion attacks work, and which is not the main purpose of this talk, but if you're interested, you can check and we can discuss more. And the third is one of the ultimate goal of machine learning, which is generalization, right? So approach or one pipeline is called this data lens, which is privacy-preserving data generation, guarantee the differential privacy. But of course, there will be some trade-off, as Jerry mentioned. If we want to guarantee differential privacy, we need to add noise, and it will have some utility trade-offs, but we can see how we can improve or relax such a trade-off by playing or proposing some novel algorithms. So here is a very interesting pipeline. I will introduce each step individually later. So first of all, on the very high level, we hope that given the data set as an input, we hope we can generate an output of the data set which preserves some statistics so that you can still train other models on this data set to play your analysis, but you cannot infer private information from the generated output data set. How we can guarantee that? The first step is, given a large data set, you randomly split the data into non-overlapped subspaces or subsets, so that given a data set, you partition it into different parts, and you train each teacher model, which is essentially discriminator. As in several previous talks, I see we already introduced against the generative adversarial networks. So here I won't introduce GAN again. Hope everyone is familiar with GAN. So here, every discriminator, like the teacher model here, is a discriminator within a GAN, meaning that the goal of these teacher models is trying to distinguish whatever the generated data you give to the teacher model will identify if it is generated or real data, right? The real data is here. So this model actually can touch the real data, right? So this is a teacher model, and we have many of them. And then after training this classifier a binary classifier to differentiate whether it's generated data or real data, second step is we use the majority vote of these teacher models and add noise to give the feedback to a student generator data model. So the idea is that, first of all, each teacher model have been trained with access to sensitive private data set. And then they do majority vote. This is one level randomness first. And then the second level randomness is add noise. And of course, for the first level, the majority vote is actually hard in this case, because if it is just majority vote on the classification result, which is scalar, it's okay, you can do majority vote. But here, the feedback from the discriminator to the generator need to be a gradient vector, a long gradient vector. So we can see if it's a long gradient vector, then the majority vote is actually hard and can be complex, and you need to add a lot of noise. In order to achieve that, we will introduce later on with another compression algorithm to compress the gradient first, so that the compression have some randomness and the majority randomness, and add noise, another layer of randomness. All this randomness together help to be considered into the analysis of privacy, and you guarantee the differential privacy here. And the benefit of it is that if you have the the compression algorithm, the noise you need to be added in terms of differential privacy is smaller, and you can preserve better utility, and you can make some trade-off between privacy and utility. We can introduce the analysis later. And after you aggregate and add noise and to the student model, then you actually get the feedback, which is the student generator will get the gradient, like the noise gradient from the teachers, and the student generator will generate the data and give feedback to them, and they can update and then go forth. Essentially, you will be able to train this student generator. And the idea is that once you generate this student generator, you throw out all the teachers which has access to the private data, and then here given this model, you only give Gaussian noise to it, which is totally private, and it will generate data for you to satisfy certain statistics of the real training data here. And that's overall the pipeline. And of course, there is some interesting thing in, as I mentioned, the compression, which we hope to decrease the high dimensionality, for example, if we want to generate image, right? And then the aggregation is trying to guarantee differential privacy. And here, based on the analysis, here is compression, which is a top K. So very interesting in SGD convergence, if you are familiar with it. So basically, if you do top K as a compression and you do the stochastic gradient, actually, I will not go to detail about it. The idea in this slide is let you know that how the compression on the high level works. With such randomness, you can not only gain randomness to protect your privacy, but also have the benefit of prove the convergence of your model because of this stochastic randomness, so that the benefit is not only for privacy, so you can actually prove differential privacy through the path of to satisfy differential privacy, which is one type of privacy guarantee. And of course, there should be better guarantees so that we can achieve better utility. And in terms of the model utility part, this is a long equation. We don't actually need to focus on it. And the idea only want to show is focus on these two terms. This whole thing shows the convergence of the pipeline we just showed. And there are two terms. And you can see the K, which is a top K compression you select in your algorithm, actually makes the trade-off between the DP and the utility. What I mean is that if you have, say, smaller amount of top K, you will lose some, you will have very good DP guarantee because you can add small amount of noise, but you will lose some convergence benefit here, so your model will not have good utility, and otherwise vice versa. So there is a good trade-off, and how to select this K will be kind of empirical selection based on the data set and based on your requirement about privacy level, about utility level, trade-off, etc. And some quick result here is that these are all the image data set. And why? Because to me, I think currently one types of main challenge about privacy preserving data generation is that it's very hard for high dimensional data. If it's like categorical data, maybe you can still have some randomness, but for high dimensional data, but naively, if you want to guarantee differential privacy, you need to add a lot of noise to every dimension, and you use your private budget very quickly, right? Therefore, this is a big challenge. Therefore, we mainly focus on image data, and this place 365 is a large, 1,000 by 1,000 dimension data set, and this is a face data set, etc. And if you are familiar with differential privacy, the epsilon delta set the level of privacy. So smaller epsilon means higher privacy guarantee. And you can see here with different epsilon, like 1 and 10, which is small and large. Correspondingly, you have different utilities. And this column is what I just explained for the pipeline, and others are the existing baselines. So you can see usually it achieves very high utility compared with others, especially during the small epsilon, which is high privacy regime. And if we consider extreme case with very small epsilon, like smaller than 1, usually we actually need the smaller than 1 level of epsilon to guarantee strong privacy. And then you can see still we get certain level of utility, but of course it drops. So how to make this trade-off between utility and privacy, I think, is still active area that we should focus and ongoing. So this is the part of the privacy, and hopefully we get some also ideas, and hopefully this is part of connection with Jerry's talk as well, and we can discuss more on the data generation. And next, with some time, I want to focus on the robustness part in addition to privacy. So because in this trustworthy machine learning world, really security and privacy, I would say, are almost equally important. Privacy, we protect individual sensitive data, and security, we save people's lives, right? And therefore, let's look at some security cases and see how we can actually say, from the example of autonomous driving perspective, how we can save people's life by doing stress tests for the security of autonomous driving. So some examples first on the high level. So we know, so in terms of the data generation in this part, I will talk about two types of method. One is optimization, one is knowledge enabled. So basically from the optimization perspective, yes, maybe many people have seen these types of adversary example, which means if you have an image and you optimize certain noise, you add to it, and you can, with this one to human, it looks similar with input, but it can actually attack a machine learning model, a well-trained machine learning model with a very high confidence to misclassify the model prediction, right? And in real-world case, not sure, maybe some of you have seen the example in our previous work, is that we can actually optimize certain spatial constraint perturbations onto this types of road signs. For example, each column here shows different types of optimized perturbation, like we call it physical perturbation. And each row here shows different physical conditions, like different distances, angles, etc. And all of the stop signs in these slides are misrecognized as speed limit sign 45 by a real autonomous driving vehicle. And the right turn sign here is misrecognized as stop sign, which we call the targeted attack. And you can see this is really dangerous if we actually put such a sign in on the real world. And for human, we actually think this is just a graffiti or random patterns, but actually they will lead to real problems. I have some quick examples about if we put this on the road. You can see on the left-hand side, this is the text one. So from the caption, you can see this one is always misrecognized as a speed limit sign 45, even the car is driving towards it. And on the right-hand side is always stop sign as a control experiment. And this can be attacked for different types of models. The first one is classification. Second one is object detection, that this is a YOLO. You can never recognize this stop sign, although you can still recognize all the objects around it very accurately, which means that the model is very targeted and it's not totally fooled. So it's very hard to identify there's something wrong with this model, right? But still, you will be fooled. Unless you go to very close to this sign, you identify the stop because it's recognized the letters. But we on purposely do not cover the letters because otherwise it's not very useful, right? And this is a white box case and a black box case, which means you don't have access to the actual model, but you just use the same perturbation and test against a different, this is fast RCN, and you can see still you cannot recognize the stop sign unless you go this close to the sign, which is too late for the car to stop, right? So basically, these types of physical, say, adversarial attacks or safety critical scenario is actually, this one is actually exhibited in the Science Museum in London, and if you have chance, I don't have the chance yet, and you can take a look, and it's very interesting. So after this, I would say from the camera, image perspective, these types of adversarial data generation is really concerning in terms of security. So people start to use this for stress test for autonomous driving, and not only against the image sensor, but also against the other sensor like LiDAR sensor, right? So here I want to show this is a real-world LiDAR with a complicated pipeline, which is not an end-to-end differentiable model. But still, I will not go too detail about it. Basically, the idea is still we can optimize the 3D point cloud shape from the optimization perspective and generate some weird shape of the object that you can put it on the road. And here is the object shape, and you can see the LiDAR on the left-hand side, which is on Apollo, that is real-world, like open source autonomous driving systems. It can never recognize this object, which we optimized and 3D print and put on the road. And in the control experiment here, if we put a box with similar size, you can always see the green box here, which means the LiDAR can always recognize it. Which means, indeed, if you put such a, like that's called adversarial object in real world, the LiDAR cannot recognize it, even human can. So that's really dangerous for the autonomous driving scenario. And similarly, if we put it onto the different position on the left-hand side, you can see you cannot recognize it, but in the control experiment, you can see the green box here of the box here, and actually you can recognize it. And not only for the camera LiDAR, but also people worry, concerned about sensor fusion systems. There are many papers talk about sensor fusion, whether that can improve the robustness of the model, etc., for autonomous driving. Therefore, here from this joint optimization pipeline, which means you can not only optimize the texture of the object to fool the like camera system or camera sensor, but also the 3D like shape or point cloud of the object, you can fool the LiDAR systems and jointly together and minimize their loss in terms of the stealthiness. And you generate an adversarial object like this. And if you run it, put it into a real-world simulation environment, one is for the LG simulation, one is for Apollo. And you can see in the bottom one, if you directly drive through this optimized adversarial object, as we just did from the pipeline, you can see the car directly run into it, which is quite dangerous because you cannot recognize this object. But if you, in the control experiment, you can see actually if this is a clone here, you can recognize it and stop. So there are many similar examples here. Due to the time, I won't to go to detail, but if you're interested, actually you can play online from our website. And this has been adopted by many autonomous driving companies for the stress test. And we actually also host a blue team competition this year in IPS, which is you can play the red team, that you can build up your autonomous driving algorithms. And we hold out some scenarios that we test so that you can test your autonomous driving algorithms with our safety critical scenario and see whether it can bypass it or how safe it is. So this will largely reduce the testing time for autonomous driving industry. And in all these examples, I mentioned some algorithms or examples or methods from the optimization perspective in terms of optimize the attack and minimize the stealthiness of the generative scenario. And I will use maybe 2 or 3 minutes to slightly introduce another one from the knowledge controllable generation perspective to generate the safety critical scenario, which means not only optimization, but also in real world. For example, still take the example of autonomous driving. We have some knowledge as human, right? We know the car should have some interval with each other, and the car from the same lane should drive along the same direction, etc. A car should not fly in the air, etc. But when we directly using optimization model to generate it, it's really hard to actually controllable satisfy these types of knowledge. Therefore, there are some structures we can leverage to encode the human domain knowledge into it. For example, from the first pipeline is using knowledge that you can use a tree-structured autoencoder. That means each node can represent some, say, object. And the tree structure means if you are on the same, like the color measure some attribute, like the color represents which lane you are in, and if you are in the same lane, you should drive on the same direction, so you have your parent satisfy the same attribute. And other knowledge you can include is causality. Basically, you can given a causal graph from the human perspective, or you can actually use some like intervention method to generate a causal graph and use that to guide the generation of the real-world scenario. So basically, you can see. what you can see here is from this trick structured autoencoder, and say if you have knowledge, say the car in the same lane should drive along the same direction, you will enforce the colors of the parent and the child node to be satisfy these types of properties. So then you can first train the autoencoder tree, and then you search over the embedding space to generate it. And these types of method, you can compare it with different, like without this knowledge, you can directly train this autoencoder tree or other like differentially, other like adversarial generative models, etc., or reinforcement learning generation pipeline to generate it. And under different scenarios and different knowledge, just want to quickly show that over the years, people are trying to generate safety critical scenario to satisfy both stealthiness and the realism. And this approach, the autoencoder tree structure approach, actually achieve the state of art that you can achieve high likelihood similarity with the real world collected data, but also the highest safety critical problems, so that you can test the autonomous driving vehicles effectively. Okay, overall, in this talk, I mainly want to talk two parts, like the security, robustness, and the privacy perspective data generation. And of course, if, as we mentioned, if we can improve this tool, the generalization will be improved as well automatically, and we have some proofs from both directions how this can be benefited from others. So overall, I think this whole trustworthy machine learning and data-driven area is connected overall area, and we have any like new discoveries and understandings from one will definitely benefit the other, and we should do research in a coherent way rather than like individual way. Yeah, thank you everyone. Happy to take questions.
Do you have any questions?
Thank you. Just a curiosity, so the adversarial examples that you showed, are they can fool any specific machine learning model, or in general they fail all object detectors? Point of asking is that for a self-driving car, can we use redundant models like 2 or 3 and hope that one of them work?
Yeah, that's a very good question. Yes, the quick answer is usually it have very high probability to fool one and for all other object detector as well. And the reason is there is something called adversarial transferability, which means you attack model A and use the same attack to test on model B and C and D. Usually it have high probability to attack, and the such B and C and D can be trained with different data, can be of different architecture, like a deep neural network versus k-nearest neighbor, even logistic regression, and it can be start from different random initializations. So that's quite surprising, and the underlying intuition about that is we know like the models have some hyperplanes, and if a model is good in terms of binary accuracy, no matter what structure they are, they usually have some underlying structure in the overall embedding space, for example, and they want to classify them or detect them. Therefore, as long as their hyperplane is close, then of course you attack one, you easily attack the others. And this is actually a very active research area about adversarial transferability, and we actually prove something about when and what's the upper and lower bound of this transferability given the property of two models. So what we show is that if the two models have high binary accuracy and their smoothness is satisfy certain thing, you always have a higher lower bound of the transferability. Meaning, if the model is non-smooth, very non-smooth, then the transferability could be very high. But if they are very smooth, actually, you can have some way to diversify them so that you can use ensemble to improve the robustness. Therefore, say, the idea is that think about the two deep neural network with two gradient, right? If they are smooth, the gradient is orthogonal, like a straight line, for example. They are close, then you pass one, you pass the other. But if they are very non-smooth, then you actually pass one, they can be orthogonal, it's hard to pass the others. So basically, this line of work actually contains different perspectives of machine learning models. And the transferability is, if you don't control anything, it's very popular in real world. You can see it attacks all models. Yeah.
Other questions? Actually, I have a question. Can you talk a little more about the ability to generalize to the possible attacks? Specifically, my understanding is that, as in one of your examples, it only requires a small amount of perturbation, which often is not discernible to the human, but can trick the autonomous car. And it's just unclear to me how you can generate enough scenarios to stay ahead of the adversaries. Like, how do you deal with that back and forth? Because I could see generating scenarios. So you synthetically generate all this data to try to improve the robustness of the model, but then somebody else, to some extent, it's almost like there's this human version of a GAN going on. I'm just curious how you think about that.
Yeah, exactly. A very good question. Indeed, in traditional security, we always have this cat and mouse game. New attack, new defense, new attack, new defense. For example, for these types of attack, if we use them, put these samples into the model, retrain the model will be robust against them. But of course, you have new types of attack like this. So that's another line of research which is called certified robustness. That also we did a lot we have a leaderboard of certified robustness, which means given some constraints of such attack, for example, the magnitude is restricted by something, or the regions is restricted by something, then I can give you the lower bound of the accuracy of the model, which means as long as your perturbation satisfies this property, no matter what new attack you generate, you cannot lower down that model accuracy than this thing. So that is promising, but so far it's still restricted because for high-dimensional data, currently the state of our certified accuracy is, say on ImageNet, it's about 27% in terms of L2 norm, like 0.05. So it's really like not very useful, but it's a good step that we can provide guarantee certification. So we really hope next step we can give better other ways. Yeah.
And to what extent can you integrate kind of hard rules to augment the machine learning? Like it's always an octagon, it's always got some percentage red. I wouldn't necessarily need a machine learning application to understand that. I mean, in fact, I could work with the local governments to ensure that certain things are always true. I mean,
actually, exactly. That's a very, very good question, and that's one of my main research focus now, which is integrate domain knowledge and logical inference to machine learning model. Not only data-driven, because indeed with pure data-driven, there are some information that is not modeled by data. As you said, as human, we can say this is octagon shape, it's a red color. It's, of course, even I don't see the stop letters, I know it's a stop sign, but machine learning model don't know that. Yeah, there's no way we can allow them to do that unless we purposely incorporate domain knowledge. So we have some pipelines. I just don't have time to talk about that in this talk, but we have some pipeline called sensing reasoning, which is sensing part, you use statistical model, deep neural network or whatever, SVM. And reasoning component, you use some statistical graphical model, like Markov logic networks, Bayesian networks, that you incorporate rules. For example, if you see, you predict this thing to be stop sign, it need to be octagon shape. If you predict it's stop sign, it need to be red color. If you have seen the STOP letter, it should be stop sign. So these types of logical rules, and incorporate into Markov logic net, for example, and connect with neural network. And you have this pipeline, and once the stop sign is attacked, although there's no way currently to detect it, but it violates the rules here in the reasoning component, and then it automatically lower down the prediction confidence of the stop sign if it doesn't satisfy the rule. Therefore, you recover it. And we show that we can achieve good, very high, almost twice of the existing certified robustness. And in pure robustness, like 40–50% improvement in terms of empirical robustness. And also, the nice thing about this pipeline, as you can see, is related with your previous question, is it's not related to concrete attack, like adversarial training or things. Therefore, you can use this pipeline to robustify against any attacks types. So it's also very helpful. So indeed, and another nice thing for this is the rule here is only for security checking, but not for doing inference. Like in the traditional AI, we have all the rules, so we need to, therefore we don't need a lot of rules here, like in traditional AI. So we only need some key rules that as long as they are violated, you are wrong. Otherwise, you go past, you achieve similar performance with the only sensing model. Right? So therefore, you don't need all the rule like in traditional AI. If you miss one rule, your performance drops. So there are a couple of benefits, and indeed, I totally agree. We should incorporate some reasoning, logic ability like human knowledge into the machine learning pipeline so that to assist the machine learning to improve robustness or whatever other things. Yeah.
Great, thanks.
And then, I mean, maybe it's similar to what you explained, but for example, humans also like to, try these things obviously to the max. So, I mean, the machine learning model could predict the stop sign correctly, but it could be that somebody put a pillow in the back window of their car, for example. How do you then know at what situation that should be treated as a stop sign versus not, obviously? But I mean, people are going to be testing this insanely, I guess, in the end, right?
I see. Yeah, that's a harder types of adversarial cases. So here, the adversarial cases, actually, the implicit definition is that human cannot be fooled, but machine learning can be fooled. We want to solve this case first so that we hope we don't, the reason we care about this case is, like, for example, for a stop sign here, if human look at it, it's no problem, it's normal, then human will not replace it. Then if the autonomous driving vehicle coming through, it will be dangerous. But if it's too obvious, like everything is damaged over the sign, like it's a blank, then human will replace it. So it's relatively safer. But if some cases, as you said, both human and machine are fooled, we need to add some constraint there. Like if we put a pillow, everything is stacked, then it's really dangerous. We need to rely on LiDAR or other sensors. But we need to consider like the threat model here that is either restricted only to machine learning or restricted to certain availability of human and machine learning, and whether there's a chance that they can jointly human machine learning work together to get the results secure and other private and things.